Hi there. This is gonna be one more video about the determinant. Why am I bringing this up again? I made a other video about the determinant, but I didn't actually tell you what the determinant is. And of course, you can basically follow them and follow the method I basically show you to find the determinant of 1 by 1 matrix, 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, and even a 5 by 5 matrix. And do it and find a number like a scalar, and the exercise is going to be over and you're going to be happy. But don't you want to know what the number is, like what the scalar that you have just found, what the value that you have just found is, like what the determinant really is? I think it's very important because you can have a visual understanding of linear algebra, not just doing computations without really knowing what you're doing. So I'm basically gonna tell you a little bit about the determinant. So let's start with the basics, shall we? So in linear algebra, whenever we are dealing with vectors, we basically start with the basis. And the main basis is the most important one, and it's going to be given by our vectors, our base vector, our unit vector. So I hat and j hat. So those are our unit vectors. Of course, you can choose a different basis, and there are matrices that can do a change of basis and stuff like that. But let's start simple. So I hat and j hat. Those are our unit vector, our starting vectors. So there we go. This is our our starting space. And those are basically our unit vectors. So what is the determinant? Well, if we basically have, I don't know, things in space, like, I don't know, an object here, and an object here, and an object here, and stuff like that, and we apply a linear transformation, like a matrix of linear transformation that we're going to call A, okay, to this space, we're basically going to end up with a different space. So we're basically working in R2, so in 2 dimension, and therefore this matrix is going to be a 2 by 2 matrix. So let's suppose that A is a 2 by 2 matrix of linear transformation. We apply a linear transformation to our space, and this linear transformation is shear. So 1, 1, 0, 1. So this is a 2 by 2 matrix, and this is a shear. This is basically going to be our transformation. What I mean by that? Well, what the shear does is to transform the space, and of course it's going to be a linear transformation. You can't do different kind of transformation are not linear in linear algebra, only linear transformation. What does it mean? That well, basically means that the origin, so 0, has to be fixed, and lines have to be evenly spaced. So those are the two properties that have to be maintained in order to apply a linear transformation. So let's apply a shear, which is a linear transformation. So basically, our space. Oh, so, I'm sorry. The space is basically gonna just the I'm used to draw this. So basically, our space is gonna become roughly like this. So basically, I hat is gonna be the same. It's gonna stay exactly where it was, like here, but j hat has been rotated like this, so it's no longer like this. So it's no longer fixed in place like in the space we started with. So this is our new j hat, right? So what is the determinant? Well, if we basically compute the determinant of this matrix, Oh, this is a very simple one. This is a 2 by 2 matrix, and we see the determinant, which is basically going to be 1 times 1 minus 0 times 1. So determinant of A is 1 times 1 minus 0 times 1, and which is basically going to give us 1 minus 0, so 1. We basically find that the determinant is 1. So these actually tell us that the determinant is 1, so is positive, and the area of the object that were in this space that are gonna be now in like this, you know, gonna be like this. The area of those objects is going to be scaled by 1. So it's basically going to stay the same. You know, we basically have just rotated, but the area of those objects are going to be the same. Is going to be the same. So it's still going to be, if the area of this was, let's say, I don't know, 2, the area of this one is still going to be 2. Okay. If the area of this one was, I don't know, 3, this one is still gonna be 3. So basically the determinant tells you how much you're gonna scale the area of an object into space. And I know what you're thinking. You're thinking, all right, it makes sense, but what happens if the determinant is negative? I mean, I can basically have a negative determinant, so what does it mean for the determinant to be negative? Well, this is actually pretty, it's not intuitive, but it can happen. So let's suppose that the determinant is actually negative. So if it was going to be -1, it basically means that the area is still going to be scaled by 1, but there's been a flip. So, you know, this one, it wasn't actually going to be like this, but it was going to be like this, like it was, you know, rotated but the other way around. So basically, let's imagine that you have a piece of paper here, all right? So this is my piece of paper, okay? And I apply a linear transformation, and I get the determinant of the matrix of linear transformation, and the determinant is -1, okay? It basically means that the area is going to be scaled by 1, but it's going to be, you know, like rotated, like this. It's going to be rotated. So the linear transformation actually rotates the space, all right? So this is what it means for the determinant to be negative. Just one more thing, and this thing is actually that what happens when the determinant is 0? Well, when a determinant is 0, you basically have a matrix of linear transformation that squishes all the space into line or other things, because, you know, let's suppose that you have, you know, our starting space like this, and we still have whoops, and we still have hi-hat and j-hat, all right? So if the determinant, and we have our matrix B, didn't want to do it in green, I want to do it in black. Okay, so we basically have B, our matrix of linear transformation, and B, let's suppose that the determinant of B is 0. Okay, so we're basically starting in R2, and this basically tells us that B brings everything into R1. What is R1? Well, the number line. So we no longer have the XY axis, we only have the number line, so R1. And this is actually going to be, you know, our hi-hat and our, I don't know, like j-hat. Okay, so basically everything is has been, you know, everything has been transformed from R2 to R1, so to the number line. And what happened if you were, I don't know, like in R3? Like if you were in R3, it was basically going to be the same. You know, let's say you have an object like in R3. Okay, so this is our beautiful object in R3, and we have a vector pointing here and another vector pointing here and so on. The matrix, if the determinant is 0, it basically means that two things could then happen. The first thing is that everything has been mapped to R2. So we basically have from R3 to R2. So if you were going to see it from an R3 perspective, all these was going to be, you know, just brought to something like this, like, you know, a plane. So basically this was going to be brought and mapped into R2. But it could also mean that everything was going to be mapped into R1. So basically this one was going to be seen from an R3 perspective, like brought to, I don't know, like this, like a line, a straight line. So everything was going to be brought to the number line. Okay, so from R3 to R2 or from R3 to R1. So both of them are going to give determinant 0. Why? Well, because in R2, the determinant actually gives us how, you know, how much the area is going to be scaled. But in R3, it's going to give us how much the volume is going to be scaled. So what does it mean that the area is going to be scaled by 0? So it's just 0. Well, it means that the area doesn't exist. And it makes sense because in the number line, the area doesn't exist. What does it mean for an R3 to have determinant 0? Well, it means that the volume doesn't exist. And it makes sense because in R2, the volume doesn't exist. The area exists, but the volume doesn't exist. And of course, in R1, the volume doesn't exist as well. So both transforming R3 to R2 and R3 to R1 are going to give a determinant 0. And in order to find out what a matrix of linear transformation is going to do by, you know, morphing the space in those terms, we have a better method than the determinant. We have the rank of a matrix that I already showed you before. So this is basically what the determinant is. So whenever you find, you know, a number, a scalar, out of the determinant with the method I basically show you, just keep in mind that that number is, if you are in R2, is how much the area is going to be scaled. And if you are in R3, is how much the volume is going to be scaled. If it is 0, it basically means that whenever you are, like in R2 or in R3 and so on, that matrix of linear transformation that you just calculate the determinant of is going to bring that space into a lower dimensional space, like for instance from R3 to R2 or from R3 to R1 and so on. If that determinant is negative, it means that it's going to be scaled by that number, but there's been, you know, a flip, like a flip of the space. That's kind of tricky to show you with, you know, pen and paper in R2, and even more trickier to show you in R3. But this is actually what you have to imagine. So a flip, you know, a flip. And this is basically it. So I want you to think about this, because understanding this is one of the main thing of linear algebra. Not just a determinant, but things in general. Whenever you see a matrix, you have to think about the matrix as a matrix of linear transformation. Whenever you see a determinant, you have to think about how much area or volume it scales. If you see, I don't know, a system of equation, you don't have to think about them like a normal, system, but you have to think about them like where the vector, to find, a vector that is gonna end up in a position with the matrix of linear transformation applied. So if you find things like, I don't know, a matrix like A1, A2, A3, A4, A5, A6, A7, A8, A9, time vector x, x, y, z equal to c, so c1, c2, and c3. This is a system of linear transformation. This is our matrix, and I want you to think about this matrix as a matrix of linear transformation. So it's gonna morph our space. X, Y, Z, we have to find them, and C, we have where they're gonna land. So the question is, where we gotta find the vectors that in our starting space, so with the starting bases, that are gonna land on those 3 points when we apply this matrix of linear transformation, and so on. I really want you to think about those things, because I really think that they're very, very important into understanding linear algebra, like, deeply. And if you just do normal computations, yeah, you're fine. You almost surely gonna pass your course and your exam, but I think that something is missing. So I really want you to think about this. All right, I hope it helps to give you an overview about what you're doing and why you're doing and what you basically find when you're doing those kind of things. Yeah, this is pretty much it. So remember,